Okay, let's continue. So we were looking at how all of these perfect fourths are going to be assessed in the next step, and we're really almost there. As it turns out, again, as you recall, the fourth root of 32, although 32 is not a perfect fourth, because 16 and 2 are its factors, and then from there 16 is a perfect fourth. We take the fourth root of that and get 2. We look at our a to the ninth, recalling that a to the eighth times a to the first is a to the ninth. A to the eighth is a perfect fourth. I broke it up, though, in two different ways. I said a to the fourth and a to the fourth. So we've got the fourth root of the first one being a, and the fourth root of the second one being another a. Keep in mind that a to the first is going to be stuck under the radical. And last but not least, b to the 20th, because 20 is nicely divisible by 4. 20 divided by 4, of course, is 5. 1, 2, 3, 4 factors of b to the 5th. The fourth root of those 4 factors ends up being just b to the 5th. And we're not done, obviously, because again, as I noted, we still are left with what? The fourth root of the 2 from right here when we first broke up 32 is 2 and 16. The a, and that is it. The b, as we said, is simply, because it's a perfect fourth, is simply noted as such. The final answer, when we put it all together, is 2a squared b to the 5th times the fourth root of 2a. And there you go. Number 3. In this particular problem, we have a square root. Again, we don't see the 2, but that's implied to be a 2. So the square root of 75, x to the 4th, y to the 7th. Let's first break down 75, as we hopefully remember, 25 and 3. And because 25 is a perfect square, we say 5 times 5. Boom, we'll highlight that. And yes, we'll easily be able to take the square root of that. X to the 4th, that is also a perfect square. As we hopefully can assess quickly and easily, x squared times x squared. Each individual x squared on its own is a perfect square. But I'm going to highlight both, and we'll say that the square root of x to the 4th will just be one of those x squareds. That's another way to think about it. Because it's a square root, that's easy to assess. Y to the 7th, I'm going to break down kind of like I did the last problem with a to the 9th. The number that's closest to 7 that is divisible by 2, again, the index or root, is 6. So y to the 6th and y to the 1st. Y to the 6th times y to the 1st is y to the 7th. We're not done. I would like us to then also, though, say that because y to the 6th can be broken up as such, y to the 3rd times y to the 3rd, we'll go ahead and assess that as the next perfect square. We're not done. Now we're going to go ahead and now take, as we did before, the square root of 25, which is 5, the square root of x to the 4th, or in this case, x squared, and then the square root of y to the 6th, y cubed. The resulting square root, which we cannot forget about, still has a 3, and it still has a y. And again, that's because we had a 3 that didn't pair up with another 3, and we also had a y that didn't pair up with another y left. Therefore, because those are not perfect squares, they're under the radical in your final answer. So 5x squared y cubed times the square root of 3y. Number 4. I'm going to go ahead and attempt to use the quotient property here, and in doing so, I'll split the problem up as 2 separate roots. Okay. So the nice thing about doing this, right away, you can see hopefully that the square root of 36, that's just 6. 125, well, that's not a perfect square. However, we can break up 125 as 25 and 5, and then 25, of course, that being a perfect square, we'll write as such, the square root of which is 5. What that's going to let us do now is rewrite the denominator as 5 root 5. So now we simply have 6 over 5 root 5 instead of what we originally had. Now, let's recall what we had done in our very second example, the very top of our notes. We had rationalized the denominator, and the reason we did so is because we had a root in the denominator. So I'm going to do the same type of analysis. I'm going to multiply both numerator and denominator by, in this case, root 5. Because we can't just leave a radical in the denominator, multiplying by root 5 is going to work out great, and here's why. 6 root 5, that's going to be the numerator. But in the denominator, we're going to have 5 times, and then root 5 times root 5 is root 25. Square root of 25, 5. Now, as you can hopefully see, we'll be left with still 6 root 5 in the numerator and in the denominator, 25. No longer do we have a denominator with a root. Let's move on. Number 5. In this particular problem, we have, as it turns out, because it's a fraction again, we have the ability to split it up as two separate roots. And again, the benefit of this is if we in fact have any perfect squares, we can differentiate, but then of course later, possibly, and it looks like we will, rationalize the denominator. Let's continue though, really with just looking at 98 in the first place. We know 98 is 2 times 49. From there, 7 times 7. So right away we can see a nice perfect square right with that particular breakdown. A to the 6th is a perfect square, and I'll write it as a cubed and a cubed. And I can stop there because I have 2 of the same thing. And then lastly, well, b to the 3rd. We know that b to the 3rd is not a perfect square, but we can write it as b squared times b to the 1st. And yes, b squared is a perfect square. If you wanted to take that extra step and write it as b times b, that's perfectly fine. Our next step is going to take shape as such. So the square root of a to the 6th is a cubed. The square root of b cubed, or we'll say the square root of b squared technically, is b, keeping in mind that we're going to be left with still a b in the numerator under the root. The denominator is interesting again, kind of like what we saw in number 4, in that we can take the square root of, in this case, 49, which is 7, but we're still left with that root 2 in the denominator. So, what we do in our next step, because again, we recall that we cannot leave a root in the denominator, we multiply numerator and denominator by, in this case, square root 2, just like number 4. So, in the next step, we do the math, and the analysis works out where a cubed b. The b and the 2 there under the roots can be multiplied as one root, so root 2b. And then the denominator will have 7 times square root of 2 times square root of 2, or square root of 4. Square root of 4 is 2. 7 times 2, 14. Final answer, a cubed b times the square root of 2b, all over 14. We'll finish up with number 6. Okay. There's not a whole lot of room to do number 6, so what I'd like to do maybe is write it here. And I apologize, but I think this is going to work out just fine. So let's go ahead and start the process of maybe rewriting this whole single root as 2 separate roots. This is going to work out very well. And here's how. Just like before, we can take, in this case, we have a p to the 5th. Now, p to the 5th is not a perfect cube. However, we can think about it as p to the 3rd and p to the 2nd. Well, gosh, here's a perfect cube. Q to the 3rd is on its own a perfect cube. And then, well, gosh, we can also mess with or play with the denominator. In this case, it's the cube root of 40, in which we can write as 8 times 5, and then 2 times 2 times 2, which is nice. There's a perfect cube again, which is our goal. All right, in the numerator, the cube root of p cubed, that's p. The cube root of q cubed is q. I'm still left with p squared in the numerator. And that's obviously under the cube root still. In the denominator, I've got the cube root of 40. We said we've got a perfect cube with that 8, so the cube root of that being 2. We're still left with, however, the cube root of 5. As I indicated in numbers 4 and 5, you cannot leave a root in the denominator. So we're going to multiply numerator and denominator, in this case by the cube root of something. Now that's something. This is probably the most challenging part of this entire lesson, certainly this problem. We want to multiply, just like we did here, number 5, multiplying by root 2 over root 2, and on number 4, multiplying by root 5 over root 5. Again, that's rationalizing. So I'm going to rationalize, but instead of multiplying by 5, I'm going to multiply by 5 squared. In this case, what is about to happen is pretty great, and that is, well, PQ is as is still. You're going to be left then with the cube root of P squared, but you still have to contend with this 5 squared, so you can multiply it by 25, and maybe what I'll do is I'll put that in front of P squared. So 5 squared being 25, there it is, 25P squared. And in the denominator I have 2 times, I've got 5 times 5 squared. Now let's think about this. Why did I, instead of multiply by 5, multiply by 5 squared? Well, if you think about it, I actually now have the cube root of 5 cubed. And what's the cube root of 5 cubed? 5. So my final answer, when it's all said and done, everything considered and simplified, looks like this. And of course, we no longer have a denominator that has a root. This concludes our lesson. I would like you all to complete, if you haven't already done so, page 33, numbers 1 through 13. I will be providing more insight when I return on Thursday, so please pay attention to that, but also the sub will provide very specific instructions for all classes Tuesday or tomorrow.